On November 2nd, I attended a public lecture by Laura Cadenati and Deirdre Shoemaker discussing 100 years of Einstein's gravity. Shoemaker spoke first about astrophysics and gave a brief history of Einstein and gravity. She explained that much of astrophysics is driven by cosmology in the expanding universe, black holes, and gravitational waves. These were discussed more in depth throughout the remainder of the lecture. I learned that 110 years ago, a key concept was established that gravitation essentially equals acceleration, which explains the concept of acceleration due to gravity at 9.8 meters per second squared. And Shoemaker also explained that the gravitational field only has a relative existence because, she used this as an example, for an observer freely falling from the roof of a house, at least in his immediate surroundings, there exists no gravitational field. Einstein established the universally known theory of special relativity, also known as E equals mc squared, where c is the speed of light and E is energy. She also briefly addressed the photoelectric effect, which occurs when electrons are released after light is shown onto a metal. These electrons are called photoelectrons. I thought an interesting fact from the lecture was spaghettification, that from objects with a gravitational pull as much as something such as that from a black hole, the closer part of the object is pulled faster than the farther away, and there is a vertical stretching of the object. An example was given about a person being stretched out and their toes going in first and stretching the person out as they travel into the black hole. I also learned that black holes are born from the act of stars exploding. Shoemaker also addressed the consequences of special relativity, which I looked up to a further extent. Time dilation and length contraction. Time dilation essentially means that the time slows down because time isn't constant throughout the universe, it is all relative. If you are traveling faster than the speed of light, time can in fact slow down. This correlates with the fact of the distance decreasing, which is also the length contraction. Cadenati spoke next, and she discussed what gravitational waves can tell us about the universe. Gravitational waves are an entirely new way to probe the nature of the universe. In physics, it can help us answer these following questions. Is general relativity the correct theory of gravity? How does matter behave under extreme gravity? And are black holes really the black holes of general relativity? The physical detection of gravitational waves is a strain, the equation being delta L over L. Detecting gravitational waves is very difficult because the waves are so small. Cadenati ended with the fact that LIGO has resumed their search for gravitational waves this past September. This interested me, so after the lecture I researched LIGO, which is the Laser Interferometer Gravitational Wave Observatory, which is operated by Caltech and MIT, and it explained that in September, after a 5-year redesign of the program and tools, the advanced interferometers began the search again for gravitational waves. An interferometer is an instrument in which wave interference is employed to make precise measurements of wavelength. This happened on September 18th of 2015. The search has been broadened in the span of researchers, which means it now includes astronomers. This means that LIGO can just notify any of the 75 astronomical observatories that have agreed to be part of this program, and this program is a global program, and they can watch for light signals that could indicate to possible gravitational wave detections. This interested me to a great extent, and LIGO keeps updating the website, so I hope to check up on this in the future, as it seemed the most interesting to me throughout the lecture. The lecture altogether was enjoyable for me to watch and sparked my interest. Thanks for watching.